Hello, everyone. I'm Deepshil Pradeep, representing Group 26, and this is our presentation on unmasking deepfakes, advanced detection techniques for synthetic media. So our group is focusing on deepfake video detection to address the growing risk posed by AI-generated fake videos. I'm sure all of us have come across one or the other deepfake video in the last week. So it's pretty prevalent, and it's high time that we, detect these videos and, uh, ensure that we have a safer and more trustworthy digital space. So a problem statement is, a project aims to develop a transformer attention-based deepfake detection model that classifies videos as real or fake. So we want to leverage self-attention mechanisms, and the model will allow us to focus on subtle facial inconsistencies, unnatural motion, and pixel artifacts, which are pretty common in deepfakes. As a team, this project presents a valuable learning curve for us, allows us to explore, transformers, explainable AI, and also gives us the opportunity to fight against AI-driven misinformation and enhancing cybersecurity measures. Our data set for this project is from the Deepfake Detection Challenge data set, which is freely available on Kaggle. It's a pretty big data set, around 400 gigabytes, and it consists of 124,000 videos and the corresponding metadata, which says if it's real or fake. Here are a couple images down below, extracted frames from these videos. Our data set consists of the previously said video files and metadata files, and we're looking to output a binary classification, real or fake, a region focus. So we're trying to show what the model is focusing on when it's detecting a video as fake. We're actually getting an output CSV file which gives the prediction and the region focus if it's a fake video. We're also providing metrics for evaluation like accuracy, precision, F1 score, and recall. Our data pipeline is a custom processed a subset of the whole data set. We've bumped it up from 10 GB to 100 GB from the baseline model. We're doing some pre-processing to sort videos, originals and the corresponding fakes, and rerouting them into train and test folders. We're extracting 5 frames per video so that we don't accidentally miss the actual deepfake portions of a video. The data can be found freely on this Kaggle link here. So coming to the exact model architecture of a vision transformer, vision transformers apply transformer architectures to image processing, by treating images as sequences of patches. We moved from CNNs to transformers as soon as we were able to get in more data, because as we all know, transformers work really well when we have a large data set, and our data set is around 100 gigabytes. So we're inputting 224 cross 224 RGB frames, and we're outputting a sigmoid activation 01 fake probability. We were augmenting the videos before, and we're still doing that with this new model. We're doing 20%, 20-degree rotation, 20% height shift, and some share and zoom here and there. Coming to the core model pipeline, right? So we're splitting these input video frames into 16 cross 16 pixel patches, and they're flattened and linearly projected onto embeddings. So embeddings are basically n-dimensional vectors, which kind of hold the information about the patch. It kind of encodes the information for computers to learn. It might not make sense to us since it's n-dimensional, but it's how it works. Learnable positional embeddings are added to these patch embeddings so that we are able to form relations between multiple patches. I can give an example. Let's say there is an embedding for a man and a woman. If you take the difference of those, you would find it pretty much equal to the difference of the embeddings between a king and a queen. So this is how a computer kind of figures out relation and correlation between different things. And this can be extended to the patches which we are generating here. The self-attention and multi-head attention work together to form the relations. And at the end, we have a classification head, which gives us the final output. So here are some of the evaluation metrics. Yes, we ran 4 epochs, and that did take a long time. It took 6 hours for one training turnaround. We were able to achieve 95% validation accuracy, and we didn't get too much of a reduction in the test accuracy as well. You can see the reduction in the loss across epochs here. Coming to the evaluation metrics, we have pretty good accuracy, precision, recall, and F1 scores. And when we can come to the confusion matrix on the right, we can see that we have barely predicted fake videos as real. This is actually the major concern, and we've kind of taken care of that. And of course, our true positives and true negatives are wonderful here. Coming to a couple important inferences, you can see the wrong prediction on the left, and the computer or the transformer is focusing on, not very important parts of the image. And a correct prediction on the right, you can clearly see that the transformer is focusing on the face and here, the eyes and the nose of the person. Some implementation challenges. We had a large data set. We had to take a lot of frames for video, and we had some GPU memory limitations. We couldn't load all the data together. And we had, there was a lack of pre-training because these models are very expensive to pre-train. And there was a short class imbalance as well. It was 1:15, but we were able to reduce it to 1:4. We have pretty much no prior work experience, and we are proud that we could work with CNNs as our baseline and finally transition to transformers successfully. And here are some of the references. Thank you for watching.